Hello everyone, my name is Joshua Mark, and I'm going to take you through the presentation for natural language explanations for malaria microscopy. To start with, malaria is a mosquito-borne infectious disease that affects humans, and these plasmodium parasites are transmitted to humans through the bites from the Anopheles mosquitoes. And as of 2021, Uganda had the third highest number of malaria cases around the world. And in the map below, it shows the particular regions in Uganda with their percentages of malaria. By examining these blood smears under a microscope, the trained professionals can be able to count the parasites, allowing for the diagnosis of malaria infections and the determination of the parasite species and density. But however, the accuracy of this microscopy depends on the skill and experience this personnel has, and misdiagnosis can occur. And misdiagnosis can occur due to factors such as the low parasite density, poor blood smear preparation, and the observer fatigue too. And so to take you through the problem statement, first of all, in the process of malaria diagnosis, we see that there has been an advancement by employing the AI models to help identify these parasites and make classifications more quicker than just using a naked eye, which is susceptible to human diagnostic errors. And in this process, these AI models that are employed to assist in this task are black box, since they lack explainability. And this is a computational domain problem. And on top of that, the existing models don't give the underlying reasons as to why they give a particular model inference. Yes, it makes it difficult for the professionals to jot down and record these diagnostic microscopic results, hence making it a difficulty for to conclude on a particular blood sample. And there exists a field gap where these people, the existing researchers, are only focusing about the accuracy of their models, but not on their explainability. Among the related works, we were able to observe that there are 4 types of plasmodiums, that's falciparum, vivax, ovale, and mareli. But of these, falciparum and vivax are considered the most harmful, though they are all harmful. And to detect this, you use mainly two methods. That's thick blood smear and the thin blood smear. Also, in this slide, we see that here is an image with malaria infected red blood cells and that without the infected blood cells. First of all, our research is going to contribute to enhance our research, the natural language explanations will enhance the comprehension for patients and doctors, fostering improved decision making. Since all these know what's happening, they know the underlying reason as to why the model gave that, and also the results are interpretable and understandable by a normal person or a normal, not only professionals. To the existing literature review, we shall be able to demonstrate explainable machine learning techniques in the medical sector, especially under malaria diagnosis, as we are doing away with black box models, which are in existence currently. Our research aims to develop and implement a responsible intelligence system for malaria diagnosis using machine learning in conjunction with natural language explanations to explain the microscopic results that have been obtained, thereby contributing to accurate recordings and interpretation of malaria-based of microscopic-based malaria diagnosis. Other objectives are as below. And first of all, to accomplish this research, we obtained a data set from Malaria AI Lab. And in this data set, it was captured under a magnification of 1,000. And also thick blood smear images were annotated, but 7,245 objects were observed in 1182 images. This is of great significance to this project and the models that we're using. To take you through the method, this is the methodology that we're going to use. First of all, we have raw input, we have exploratory data analysis, we performed part of it to achieve the preliminary results that we have obtained. Then data processing and data selection. We split the data into train, validation, and testing. We try to train models, the YOLO V8 and RCNN models, to obtain the preliminary results we have, but also to perform this model, the model evaluation. We use a few matrices like accuracy, precision, recall, and F1 score with the confusion matrix too. But after this, we see that our models are black box, and that's what we're trying to eliminate. We'll go ahead and implement model explainability using some few explainable techniques like GrandCam, Sharp, and Line. We're using these first of all because they are compatible with Hugging Face transformers, but we also hope to use others and test others like occlusion analysis, integrated gradients, deep lift, and others. We'll also have to go ahead and generate the explanations for these. We'll have to go ahead and generate explanations for these models, and we hope to use Hugging Face with BAT as well. Then go ahead and validate and perform user testing, iterative deployment, and refinement. Also to integrate this whole system and framework into a mobile application. To take you through the preliminary results, first of all, here is a confusion matrix of one of the models, and we see that it was able to predict 25 images plasmodium, and they were truly plasmodium, and 43 as non-plasmodium, and also the actual label is non-plasmodium. This is of great value and importance. In this screenshot below, we see some evidence of removing duplicates, hashing images, and in this model, this was RCNN. In this model, we used 35 epochs because we were limited with the resources. We have very few resources, so these results were obtained on the very few resources that we have. But if we get more resources, we believe we'll be able to obtain more accurate results. The accuracy here was 70% for the yellow mode and 80-something% for the RCNN model. These are some of the techniques that we use to implement model explainability. When you look at this image here, these spots here, these dark spots, they're also clear in this image. These are some of the parasites that the model is trying to focus on. And this was GrandCam. Also using Deep Dream, this was the output, still showing the particular objects that the model focused on. We also went ahead and used Sharp and Line. And those are some of the explainable techniques that we hope to use. Those are some of the techniques that we hope to use, but we may drop Deep Dream because it's not compatible with Hugging Face transformers, which will be used to generate the natural language understandings. To conclude, there is a gap where people are using black box models, and also they don't know how to write down these results, and those are some of the things that we hope to cover. And yes, for future studies, we hope to develop a system that will be responsible for a responsible AI system. Maybe, well, we might also divert and go to other disease sectors in future. As an acknowledgement, we would like to express our deep gratitude to Mr. Gary Wangomabin and Dr. Rosemary Chibuli for their work, and also Makerere AI Lab for their data set. Thank you.